So, welcome to the second video of our second class time series of lecture videos. We ended the first one with the rejoinder that we would come back to discuss the bromination of 1-butene next. And here we have 1-butene, so 4-carbon alkene. We're using NBS in carbon tetrachloride, and lo and behold, instead of, getting our bromine at this secondary allylic position, like we might expect, so that is 3-bromo-butene, where we don't know what the stereochemistry is, so I've drawn a squiggly line. We only get 30% of that product, and in fact, we get 70% of a mixture of cis and trans 1-bromo-2-butene molecules. So we've still got our 4 carbons, 1, 2, 3, 4, except our bromine is now at one of the terminal carbons. And of course we get our succinimide and HBr. So what is going on here? Why are we getting 70% of 1-bromo-2-butene? And this has to do with, what part of the allylic radical system that we form preferentially reacts with the bromine. And we're going to launch into that discussion forthwith. So, here we go. Why is 1-bromo-2-butene the predominant product? And we've got to look at the mechanism. So we'll start with initiation. We take our diatomic bromine, we break it into 2 bromine radicals. Then, of course, propagation. We'll pluck off one of these secondary allylic hydrogens to form a secondary allylic radical initially, but of course this has a resonance form associated with it where we've got a primary allylic radical. And now it depends on which one of these resonance forms is preferred, which really is to say, which lobe, p orbital lobe, in the pi non-bonding molecular orbital of this particular allylic radical system has a larger set of p orbital lobes, because that is the one that, in this case is going to preferentially react with the bromine. So here we go. We can bump into our bromine from either this secondary allylic carbon or this primary allylic one. While this is the more stable intermediate, we end up with the more stable product, where our alkene has 2 alkyl substitutions. So this particular reaction is driven by thermodynamic considerations as opposed to kinetic ones, and we'll try to discuss that to the point where you understand whatever it is I'm talking about. Of course, the byproduct of this reaction is a bromine radical, right? So we've got a Br dot, which we're forming. Our issue of selectivity, thermodynamic control, the reaction products depend on the relative stability of the possible products, and we choose the most stable product if our reaction is under thermodynamic control. Versus kinetic control, the reaction products are formed independently of the relative stability of the possible products, and we're really choosing to go through the most stable, kinetically preferred intermediate, right, with the lowest activation energy. So this particular example is one that's under thermodynamic control, and it's important to remember the relative stability of alkenes in this section of chemistry. So an important item to recall from alkene chemistry in first semester chemistry, CHN 233, concerns the thermodynamic stability of substituted alkenes. So if you have more alkyl substitutions on your pi bond, you have a more stable alkene. So tetrasubstituted is more stable than trialkyl substituted, which is more stable than trans dialkyl substituted, which is more stable than cis dialkyl substituted because of sterics, which is more stable than monoalkyl substituted. So what I'm trying to say is R prime, R double prime, R triple prime, those aren't hydrogens, right? They're alkyl substitutions. Okay, so what is this issue of thermodynamic versus kinetic control? We've got to revisit one other subject we talked about in first semester organic chemistry, and that's the Arrhenius equation. So in 1887, Svante Arrhenius observed that rate constants vary exponentially with inverse temperature. So his equation, K equals some pre-exponential constant A naught times e to the negative EA over RT, where EA is activation energy, R is a constant, and T is temperature. Another form of this equation you might be more familiar with is the one where we've taken natural logarithms of both sides. So ln of K equals negative EA over RT plus the natural logarithm of A naught. So let's consider some reaction that can happen to B. It can either go to C or it can go to A. It goes to A with some reaction rate constant K1. It goes to C with some reaction constant K2. In theory, all reactions are microscopically reversible. We might say that A could revert back to B with some reaction rate constant K minus 1, and C could revert back to B with some reaction constant K minus 2. Well, the rate of B going to A is going to be equal to the reaction rate constant K1 times the concentration of B, as long as K minus 1 is very, very small. So what we're essentially saying is these are irreversible reactions of B going to either A or C. And similarly, the rate of B going to C is going to equal the reaction rate constant K2 times the concentration of B, as long as K minus 2, that back reaction rate constant, is very, very small. Wonderful. We have that. Let's look at a hypothetical energy versus reaction coordinate diagram for these processes of B going to A and B going to C. In terms of thermodynamics, C is a more stable product than A, right? But in terms of kinetics, that is the rate at which these reactions occur, the reaction of B going to A is going to be much faster than the reaction of B going to C. Why is that? Well, activation energy EA1 is much lower than EA2. So that's an easier hill to climb. So if we do Arrhenius equations for both these paths, ln of K1 equals negative EA1 over RT plus ln A naught, and ln K2 equals negative EA2 over RT plus ln A naught prime, as long as A naught and A naught prime are similar, we could subtract one equation from the other, and we get ln of K1 minus ln of K2 equals negative EA1 over RT plus EA2 over RT, because these guys cancel out as long as they're similar. And then we can, collapse this side to natural logarithm of K1 over K2 equals this difference in activation energies, EA2 minus EA1 over RT. And then we take each side, raise it as a power to E, and we get the ratio of K1 to K2 equals E to this difference in activation energies over RT. And we discover that, at room temperature, if we wanted to get a 10 to 1 selectivity, that is K1 is 10 times greater than K2, the difference in those activation energies will have to be about 1.4 kcals per mole. That is, activation energy 2 will be 1.4 kcals per mole greater than activation energy 1. And of course, if B going to A is 10 times faster than B going to C, you end up with a ratio of 10 times as much A as C at the end of your reaction. All right. It's definitely interesting when we have reactions that are under kinetic control or under thermodynamic control. In general, under thermodynamic control, typically reactions can be reversible and they find the lowest energy, most thermodynamically stable product. But if they're under kinetic control, then we're going to go through the activation energy, that is least high. So I think that's about where I will end this class video, and we'll take up an example of this in our third video for this class time. So I'll see you soon.